In this question, we're told that water flows from this large tank, which is 0.4 in our system, through a pipe, which is pipe 1, and this one splits into two smaller pipes, 2 and 3, which discharges 3 jets. We're asked to determine the flow rate from the tank. Okay, so the flow rate from the tank will also be the flow rate in 1, yeah. Because obviously what's coming out is going into this pipe, and also to find the gauge pressure at point 1. And as you can see from the diagram, we're also given a whole bunch of other information. So we're told the difference in height between point 1 and point 4. We're told the difference in height between point 3 and point 2, and also told the diameters of the pipes. Okay, so how are we going to go about doing this? Again, the easiest way to do this is to build up a table, okay, and see which information is missing and which information we need to kind of unlock to get the next piece of information, to get the answer. So what we're really trying to get is the pressure and volumetric flow rate in pipe 1. But before we start, we can actually make some simplifying assumptions. So first one is that we were told that the 2 pipes, 2 and 3, were discharging into the atmosphere. So we know that the pressure there is atmospheric, okay? And given that the tank was also open to the atmosphere as well, we know that the pressure in 4 is also atmospheric, okay? But we don't know what the pressure is in pipe 1. That's what we're trying to find out. Another assumption that we can make is that because the tank is very large compared to the pipe, that the velocity of the fluid in the tank is negligible compared to the velocity of the fluid in pipe 1. Therefore, we're going to say that's 0 as well. So those are the initial simplifying assumptions that we can make. So once we've got those, we can see we can now start working through to try and work out the velocities along here to eventually work out the velocity will be in this pipe. And once we know the velocity in this pipe, we can work out from the area what the volumetric flow rate is. So if we take Bernoulli's between point 2 and point 4, okay, so put in the values into here. Well, first of all, we can see that Z3 is equal to 0, okay, so we can cancel that term. We can see that we've got atmospheric pressure on both sides, so they will cancel. And also we can see that C4 is 0, so that term will also cancel. So we now just have C3, which is we're trying to find, and is a function of rho g z, which we do know. So if you rearrange this for C3 and plug in the values, you should get an answer of 11.7 meters per second. So in the same way that we use the analysis on the previous slide, we can also work out the velocity at in pipe 2. So again, we write out Bernoulli's in its entirety. Remember, we've got this static pressure term plus this dynamic pressure term plus this hydrostatic pressure term is equal to a constant. And we can cancel some terms out here because the pressure at 2 and the pressure at 4 is atmospheric. So those cancel. And we also know that the velocity at in pipe 4 is 0. And we now know Z2, Z4, and we can solve for C2. And if you rearrange and put in the values, you should end up with an answer of 7.68 meters per second. Okay, so finally we're getting there. We're getting all the information we need. So to find the volumetric flow rate in 1, we can work it out from continuity, and we know for an incompressible fluid, again, what comes in must go out. So we've got the volumetric flow rate in pipe 1, which is split into the volumetric flow rate in pipe 2 and pipe 3. We don't know what this is, but we can work it out because the volumetric flow rate is equal to the area times the velocity through that area. Okay, but at this current time we don't know the areas, but we do know the diameters of the pipe. Okay, so we can work out the area 2 and area 3. Put that into the table. Then we can now work out V1 from the velocity times the area, sum of these two. and if we do that, we should get an answer of 9.1 times 10 to the minus 3 meters cubed per second. Okay, so that's one of the things that we asked for, is volume flow rate in the pipe. And we could convert that into a mass flow rate if we wanted to by times it by the density, which is 1,000 because we're told it's water. Okay, so for the last part of the question, we want to find out the pressure in pipe 1, the gauge pressure actually we're told in the question. So before we can do that, we need to know the velocity here, and we've just worked out the volumetric flow rate. So dividing the volumetric flow rate by the area, which we can work out from the diameter, we end up with a velocity of 4.63 meters per second. So we can now have all the information we've now got all the information we need to work out the pressure at 1. So again, writing out Bernoulli's in its entirety, we're going to go from 1 to 4 this time. Now, just to clarify, so the pressure, the static pressure term that's in the Bernoulli's equation is an absolute pressure. Yeah. So, and if you remember that the absolute pressure is equal to the gauge pressure plus atmospheric pressure. So we can make that substitution in here. So this is the gauge pressure at 1 plus the atmospheric pressure gives us the absolute pressure, absolute static pressure. Okay, so we're just going to make that first substitution before we do anything. Then looking at this, we can start cancelling some terms out. So those two atmospheric pressures, we cancel each other out. We know that Z1 is equal to 0, so that term will disappear. And we also know that the velocity in pipe 4 is equal to 0, so that term will disappear. So now we know, we've got everything we know. So we know what the velocity is in pipe 1, we know what Z is in pipe 4, and we're trying to find the gauge pressure. So if you rearrange this, you should end up with an answer of 58,000 newtons.